Our third speaker today is Cees Snoek. Cees leads the Video and Image Sense Lab at the University of Amsterdam, and he's also involved with a number of AI labs with Qualcomm, with TomTom, and with the Inception Institute of AI. He will talk to us today about real-world learning. The floor is yours, Cees.
Thank you, Martin, and thanks for having me today. Yeah, I want to talk about real-world learning. It's more sort of like a vision, and I have some first work towards this direction that is of a bit more technical nature. But let's first talk about real-world learning. So we have awesome learning. Here are just a sample from recent covers from Nature and Science showing what artificial intelligence is capable of. So not only beating Go masters, folding proteins and devising chip floor plans, you name it, everything can be solved with AI, it seems. Yet there are still quite some problems on the table. So consider the following diagram where we have on the y-axis the dependence on supervision, and on the x-axis the societal impact, where I distinguish between a closed world setting and a real world setting. Now, AI is very capable in a closed world setting where there is a huge amount of data and labels is available. And AI, especially deep learning, is unbeatable. And you can do magical things, so to say. Now, the field is moving towards this direction. So following the same paradigm, expanding the closed world assumption, and we can do even more beautiful things. But there are quite a few problems. So deep learning and representation learning in general is heavily biased towards training conditions. So it means it will become brittle under more real-world situations that differ from those perceived during learning, not only in terms of data and labels, but also in terms of objectives and, as we have already heard before today, in terms of fairness measures. So simply scaling up along all dimensions at training time seems to me to be a dead end, and moreover only feasible for big tech and big states. So from an academic perspective, not a very interesting topic to pursue. Moreover, this brings humongous compute storage and ethical expenses by collecting more and more data and storing this on local servers. But there's also the human aspect, is that we humans can generalize quite robustly in a very data efficient fashion. We don't have to learn for everything we want to name. We don't have to see thousands of examples. So there must be another way. Now, several learning paradigms have been proposed in the literature to account for the limitations of deep learning with the IID assumption, right? So that training and test are from the same independent and identically distributed distribution. So one solution is domain adaptation or domain generalization, which is even harder. And in domain generalization, the problem is, given a certain set of source domains that you have seen, and here a source domain can be photographs, art paintings, and cartoons, for example, and the goal is to recognize an elephant in these data sets. Now, in domain generalization, you will be shown a target domain, let's say sketches, that you have never seen during training, and the goal is to still be able to predict the elephant. And deep learning suffers in this scenario. Another solution that people have explored is what I call the label gap. So changing label vocabularies are the topic of interest in zero-shot, open set, and open world learning, and also self-supervised learning, where people try to learn from inherent structures in the data without relying too much on huge amounts of labels. Now, the other problem is the objectives gap. So when objectives change during a learning task, deep learning has trouble. And this has been studied in continual learning and also in meta-learning context, where algorithms learn to adapt their tasks over time without catastrophic forgetting. And research is working on these solutions, but it's still early stage. And then we also have the fairness gap. So representation learning often maximizes a single scalar performance metric like MAP, but does not take into account all kinds of fairness metrics. And fairness can be taken into account before you perform any learning, like defining data sheets for data sets. So at creation time of the data set, make sure that the data sets comply to all kinds of fairness metrics. But we are more interested in learning fairness during the representation learning. And in recent work, we have shown that in an image classification setting, by adapting the feature and the label spaces, we can mitigate biases in image classifiers during representation learning. So we cannot only solve it by changing the data, but also considering the algorithm itself, which I think is very promising solution. Now, all these gaps, so the distribution gap, the label gap, objectives gap, and fairness gap, are problems in real-world learning. And as it happens, while all of these individual gaps are being attacked by particular methods, there is currently no learning methodology that can dynamically generalize and adapt across domains, labels, tasks, and fairness metrics simultaneously, and do so in a data-efficient fashion. So, in my view, this is sort of like the holy grail and the ambitious long-term goal of real-world learning. So addressing all these gaps in a data-efficient way to get to the sort of like next generation of AI algorithms. Now, in today's talk, I don't have the solution for all these gaps yet, but I want to present some recent work that addresses the distribution gap and the label gap. And that is from a recent paper that appeared in the ICLEAR conference. This is joint work with Yingyun Du, Shantong Zhen, and Ling Xiao. And this is executed as part of the AIM lab in Amsterdam. So we consider a few-shot meta-learning approach. And here the idea is that you frame a learning problem at two levels. The first one is quick acquisition of knowledge within separate tasks. So here the task is to label a query image into one of the 5 classes seen during training. And in meta-learning, you do this in 2 stages. The first one is this quick acquisition of knowledge within a task. And the second layer is essentially slower extraction of information that is learned across all kinds of tasks. And this is achieved by separating your training data in a meta-train test, a meta-training stage, a meta-validation stage, and a meta-test stage. Now, the deep learning workhorse and also the workhorse in meta-learning is batch normalization, based on a famous paper by folks from Google at ICML 2015. And the main idea of batch normalization is to stabilize the distribution of internal activations of your network during training. Right? So rather than having various distributions for all kinds of activations, you normalize it within a batch. So the main trick is to take a batch of samples and to normalize by the mean and the variance in a clever way. Now, this works well in a many-shot setting. For example, if you want to classify classes on ImageNet, but it starts to fail or it becomes unstable when your batch sizes are very small. For example, in a few-shot setting, or when there is a shift between your source and targets domains in the domain generalization setting. So the batches on which the batch normalization is built are no longer reliable or representative of the data seen at test time. Now, this is solved in meta-learning often implicitly by using a transductive batch normalization. That means that the batch statistics are computed using all available test query data points, and this is a wise way of using your data. But the requirement to have all these test samples available limits real-world users, because this is never really the case. And the first paper to pose this as a problem was work by Brondskill et al. That appeared at ICML last year. And they identified this limiting assumption of the transductive setting in meta-learning. And instead, they proposed to leverage statistics from layer and instance normalization and to blend this in an effective way, and to learn this blending as a parameter during meta-learning. They show that this is better than regular batch normalization, but still worse than the transductive setting. Now, our proposal is what we call meta-norm, and we also leverage the meta-learning setting. But what we do is we infer statistics from the support set that better match the query set. So our idea is essentially to minimize during meta-training the QUVA divergence between the distribution of the support set and the one of the query set. And by doing so, we achieve an adaptive batch normalization. So depending on the support set, we adapt our batch normalization so as to optimize it for the unseen query set at test time. Now, this slide looks a bit complicated, but the essence is really simple. So what we introduce are hypernetworks, F, that generate sample the mean and variance samples for the support set and the query set. And during meta training, we minimize the QUVA term between these two hypernetworks, the predicted parameters for these hypernetworks. And then at test time, this is a very good predictor. So during meta testing, giving a test task, we take only the support set as input, and from this we generate normalization statistics directly for the query set. Now, we have done a bunch of experiments, and I will highlight the most important ones in this talk. So here we show that this using this QUVA term during meta training is very effective for both few shot classification and domain generalization. And here we evaluate in a 5-way 1-shot and a 5-way 5-shot setting. And as you can see, that the numbers with the QUVA divergence are considerably better than without. So this works both for few shot classification and many shot domain generalization. So recall that in domain generalization, we train, for example, on art, cartoon, and sketch, and we evaluate on photo, and we rotate among these domains. Here's a comparison with other batch normalization schemes. So TBN is transductive batch normalization. CBN is the traditional, the common batch normalization as originally proposed. Task norm is an improvement, and meta norm is our proposal. And we outperform both the transductive and non-transductive normalizations, independent of the underlying meta-learning algorithm. So ProtoNets is a meta-learning algorithm, and MAML is another one. And actually, we also compare favorable for Versa, which is yet another meta-learning approach. Then we also make an effort towards real-world learning, where we consider the new problem of few-shot domain generalization. So here the task is to learn from a few examples, so in the order of 5 examples, to not only learn to classify the correct category for an image, but to also at the same time generalize across domains. So with only a few images seen from a quick draw and a clip art domain, you are still able to classify the baseball in an infographic image. So we again formulate this as a meta-learning problem. And this is the first time that this problem was defined, and we show that also in this setting, meta-norm is quite effective. So meta-norm allows for batch normalization of small batches across domains. And I think that brings me to the conclusion is that there is a need for real-world learning across domains, labels, tasks, and fairness. And meta-norm is a first approach to consider few-shot learning across domains with one algorithm. It's actually a very simple meta-learning batch normalization. It's generic and model agnostic, can be easily plug and play in existing meta-learning approaches. So I think this is promising, and we hope to report more results in this direction in the coming year. Thank you.
All right, thank you, Cees. Can you say a bit more about these other? You set up many dimensions, right? In that 2D plot at the beginning of your talk. Can you say a bit about the other dimensions that you haven't touched on with meta-norm?
Yeah, so meta-norm is just one approach that combines two of those dimensions, right? So I'm not saying that meta-norm will be the approach for all four. We have been looking into continual learning. So there the goal is to learn while doing, so to say. So you get a new task and you're still able to classify while not forgetting things that you have learned in the past. So you learn new information, but you don't forget what you have done before. Currently, all these continual learning papers consider the same objective, like image classification. They cannot learn on image classification and then do image segmentation where you label pixels or you move to video. So it's still rather simplistic in a way. So one of the dimensions we want to do the coming year is to also consider continual learning with a variety of objectives, right? And we now see some works doing fairness in vision. So we are behind NLP, so to say. So where we are now is that people take one task, like image classification, and demonstrate that biases can be mitigated. That is where vision has arrived now. And now the question is, can we make that more dedicated and also include that in a few-shot learning approach that can do domain generalization, right? So we have just shown with work that will appear next month that we can maintain image classification performance while improving upon 4 fairness metrics. So can be done, but still in the traditional regime of many short learning, right? It is far more interesting to see what can you do in few short learning scenarios and prevent biases there. How to do that? Don't know yet, but
okay,
working on it.
Okay, thanks. Another question I would have. So as you know, my background is in search and recommendation, and there we can think of the results that we return in a pointwise fashion. This is a good item. That's a good item. We can also think of them in a pairwise fashion. So here are 2 items. We think this is more appropriate or useful to you than this other item. Or we can think of them as a slate, as a complex structure. Here's a ranked list, and then of course, depending on how we formalize the problem, also some of these desiderata that we want to formulate change. For instance, in a list, you could say, well, I want a diverse list, or right. So where, for instance, if we recommend songs, I want a diverse list that have popular songs and not so popular songs, or that have big label songs and small label independent label songs. what's my question? The question is, many of the methods that we have for fixing, for instance, fairness or diversity, and for these more complex result presentations, are post hoc methods. So we first generate good items, and then we begin to sample from the bunch of good items, compose a complex list, and then that hopefully that's not just good items, but also diverse or fair or and so this is a very open question, but given that you want to go for real-world learning, and real-world learning to me means we don't have just small individual items. We have complex setups where we need to help people maybe achieve a task, and to achieve this task, we need to give them a set of options. We need to give them maybe even a sequence of options, assuming that if they first do this, then they'll need this item, and if they then do that, they need that other item. Where on your map are we with those sort of problems? More complex result lists, or sets of items, or slates, recipes perhaps even, rather than individual items?
Yeah, it's an interesting question. So I would like to take one step back. Is that in Euvision, the traditional paradigm, very similar to traditional machine learning, is that we have this notion of a train and test set. In the real world, you have no test set. The entire world is your test set, right? So I think we have to move away from this train and test set paradigm. And I mean, in retrieval, yeah, you also have a test set, and then you perform rankings, and you start to do, inside this ranking, you can do things, right? The similar things you can also do in Euvision by, there is some recent work from folks at Berkeley where they take one sample, and based on this sample that they see for the first time, they predict something. So this is they call it test time training. So you see a new image, and you do something clever on it, and then you make a prediction. The same thing you can also do fairness measures. You can also do the same thing, rather than saying, look, I apply the same measures on all images. I take a sample from my image. I sort of have a sense of what is in there, and I adapt accordingly. Now, this is one image at a time. Yeah. I think at some point we will get inspiration from IR, which is much more mature on this dimension. And we can also consider pairs, sets. And so we are looking at IR in this sense.
Okay.
Does that answer your question to some extent?
Sure. I think in an earlier discussion with colleagues also from computer vision and NLP, I thought the following was a useful observation. So what we often do in IR now is, we compute what we think reasonably useful results. We show them, and then we see how people interact with them, and then from the interactions we learn which ones are actually the more useful ones amongst the useful ones, and then so that's more of a re-ranking problem. We have a bunch of hopefully useful items, and then we learn to re-rank them to get the most useful ones on top. Slowly we're moving to a situation where rather than this two-stage pipeline, first get useful stuff and then learn to re-rank the best useful stuff, go to end-to-end learning. Is that something, and so that's where I think we should be heading. It is where we're heading because, for instance, we need to, in the two-stage pipeline, it's very hard to get over the vocabulary gap, right? Because if you need to actually settle it in the first stage, but if we don't do it, and but we can do it if we do end-to-end. I always felt that computer vision is much harder than NLP. Before we were able to find good images that we were actually willing to expose to people, but we seem to be getting there, and so that I think that also means, in my view, that we seem to be getting to a stage where instead of first getting reasonable results and learning to re-rank them, do the whole thing in one end-to-end learning setup. Is that part of your real-world learning ambition?
Yeah. Actually, I think for real-world learning to be feasible, it has to be multimodal.
Yeah.
So I consider, of course, video the most natural medium to study real-world learning, and because it comes with multiple modalities and spatiotemporal consistency, causal consistency. So then you can really exploit similarities in the data, local similarities. So that and the multimodal aspects. So that gives you very rich sources of information to build upon, right? So there is already a lot in the data.
Yep.
And that's why I think so insights from information retrieval and also NLP will be very useful, because I mean NLP is ahead of vision. I mean the transformers were first introduced in NLP and the GTP3, etc., and they are now slowly being absorbed by computer vision as well. And I mean the wave will come. So next step is to combine all this information. I mean, DeepMind is already doing things. So some labs are starting to do multimodal transformers, but everything is still based on huge amounts of data, right?
Yeah.
So what can we now do with less data? So more cleverness rather than just more machines and more data.
More cleverness, that's always a good ambition.
Yeah, I think so.
All right. Thank you so much, Cees.